folks. It's really nice to be here. So today I'm going to talk about Docker and Kubernetes, and I'm also going to talk a little bit about socks. The reason for that is that we built an application called the Socks Shop. The reason that we did that was that the company I work for, Weaveworks, is based in the container ecosystem. So we're built around Docker as an emerging phenomenon. And there are lots of other vendors in this space, and there are lots of vendor demos. Lots of people show off their technology in various ways. But while there's lots of talk about microservices, there are no actual microservices demos. All of the demo applications that you see for like Fig, which turned into Docker Compose, or Kubernetes, are typically these sort of silly little noddy things. Like, has anyone seen the Fig counter that just increments a number in a Redis database? It's like you hit reload and it increments the number n times. It's not really a realistic example. And similarly, the Kubernetes sort of canonical example for the Kubernetes application is a guest book that's just a PHP guest book written in Redis. Written to connect to a Redis database. And so we wanted to come up with something a little bit more realistic. So we built this sample microservices application called the Socks Shop. And so this is it. It's not much to look at. We're not really front-end people. We do have some good front-end people, but they didn't work on this. But it's a working e-commerce application for selling socks. And that's fine. It's kind of a good, realistic use case. It's not much to look at, but it's much more interesting in the back end. So today I'm going to talk a little bit about the goals for this application, and we can look at the application and sort of poke it a bit, deploy it to a few different places, and talk a little bit about microservices, Docker, Kubernetes, and then at the end I've got a little section on some of the internals of one of the tools that I'm going to show you called WeaveNet. So when we were building the Socks Shop, there were a number of goals. We wanted to demonstrate microservices best practices. And in fact, we ended up demonstrating microservices best practice and also some microservices mistakes. So it was a pretty interesting learning experience. So for example, we learned about when coupling is necessary. So presumably the folks here are familiar with the concept of microservices. Give me some nods. Yeah. Okay. So we learned about some of the cases where coupling was necessary. Obviously, it's nice if all your microservices can be as independent from each other as possible, so you can have different teams working on different ones. But when you're adding or removing whole microservices or changing the sort of structure of the application, there's obviously some inherent dependencies are formed because the things that need to point to the new shape of things need to change as well. So we had some issues where we forgot about that, and we added a microservice and deleted two of them, and we didn't deal with version dependencies very well. So it was an interesting real-world experience of sort of trying to practice what we preach. Another goal was to be cross-platform. So this is sort of, in a sense, perhaps slightly unrealistic for a typical user, but we figured out how to deploy the Socks Shop to Docker, Docker Compose, Docker Swarm, Kubernetes, DCOS, Mesosphere, Marathon, which are kind of the same thing, Kubernetes, ECS, and I think we got about 13 different integrations. And that was also really interesting because we got to learn about some of the differences between those different platforms. And we sort of settled on this fairly standard way of building the application such that all of the container images that make up the different microservices use the same images, and they all assume the existence of DNS for service discovery, for example. And then it's up to the platform to provide those sort of basic services so that things can be brought up, things can be scaled, things can find each other using DNS. So yeah, I would rate us pretty well on the cross-platform aspect. We've got pretty broad coverage, but support for some of the orchestrators is pretty experimental still. So it's kind of interesting if you look at the Mesos and Marathon example, with Mesos and Marathon, you're still left to sort of, at least when I last played with it, you're given quite a lot of pieces and you're expected to assemble the car yourself, if you know what I mean. So so we didn't have sort of out-of-the-box container networking. We didn't have out-of-the-box service discovery when I tried that. And so we had to add some bits to get that working. We also wanted to demonstrate the benefits of continuous integration and deployment. So we obviously wanted developers working on the SOX shop to be able to deploy changes easily to individual microservices and to have that automated at least into a staging environment so that whenever a change gets made, that deployment happens quickly. That's definitely a work in progress. We're still developing integration tests and things that allow that CI system to be more realistic, because you obviously want to gate a deployment on a failed test. We wanted to sort of demonstrate. And the other thing about continuous integration and continuous delivery is that when we were deploying to Kubernetes, we found some gaps in sort of plugging the output of the CI system into the input of Kubernetes. So it wasn't immediately obvious how to match up which versions of the code match onto which versions of the Docker images, and to be able to control the deployment of those in a sane way. And that actually led to us developing a tool that we call Flux, which in fact, Flux was developed. So the SOX shop is a microservices sample app, but we also run a production deployment of Weave Cloud, which is one of the tools I'll show you. And Weave Cloud is run on Kubernetes, on AWS in production. And it was during the development of that we really found this pain point with continuous delivery. And so we developed Flux as a tool to help with that. It's interesting as a developer tools company to be dogfooding everything we do and making sure that if we come across pain points in our own application development, then we can sometimes turn those into open source projects and services. Okay, so we also wanted to demonstrate how DevOps and microservices complement each other. And that was definitely true. We were able to work in smaller groups. We were able to a developer could fit a microservice in his or her head quite easily. And indeed, when you're not changing the structural aspects, you could independently upgrade and deploy them. But the main thing was that we wanted to provide this real-life sort of testable application for various orchestration platforms. And this is important to us because we're trying to build tools that are useful to developers who are doing this stuff. And it allowed us to really show it working for real. So this is the application, or at least when I first loaded up the application and took a look at the README, this is what I thought the application was. Now, there are various different components. They talk to each other in a fairly logical way. So, for example, we have the UI, which talks to various different APIs. Everything's REST. And at the bottom, you can see all of the different languages that are in the various different SOX shop repos. And so one of the things that we wanted to do was develop some of these services in different languages. And we succeeded. So some of them are written in Spring, some of them are written in Go, some of them are written in Node, and there's a worrying amount of shell. What I did notice, though, was when I pulled up this diagram in the README, the diagram, I thought it would be pretty useful, but it says that there's an elk stack. And when I looked around in the Docker images, I couldn't find an elk stack. So I was like, I wish there was a better way of figuring out what was actually running in my app. So that's the first demo I'm going to show you. I'm going to show you a tool called Scope that we've developed, which can show you what's running in your application in what's sort of like a live architecture diagram. So it avoids this problem of like, oh, I don't have an elk stack. So let me just try that. Okay. So I've got a Docker Compose file here, and so you can see all of the different services in the application. So you can see we've got this front end, we've got an edge router, a catalog, and so on and so on. This file is really long, so it's difficult to sort of get a sense of how the application fits together just by looking at this file. But what I did earlier was I ran Docker Compose up -d. I'll let you take my word for that. It takes a little while for all the different services to spin up on this tiny little laptop. But I can now do Docker PS, and I can see that I've got all these different pieces up and running. And again, it's still kind of difficult to see how everything fits together just from this long list. So the next thing I did was I went to WeaveCloud. So WeaveCloud is a hosted version of some of our different tools. You can also run them on your own if you want to. And the one I'm going to show you right now is called Scope. And I can just run Scope launch. And that specifies the service token. And that service token sort of ties this Docker instance to this account or instance in WeaveCloud. And so you can have multiple instances, and so you can organize yourself in a reasonable way there. So I can see that, let me just sort of pull that up. Oh. So I can see that the probe connected with this little blue dot. Moby is the name of my Docker VM, so because I'm running Docker for Mac. I can click and view the instance, and then I can see all the different components show up as containers. And so this is slightly more useful than just a straight list. You can click on one and see what it's doing. You can even get a shell inside it if you want to. If the Wi-Fi holds up. Oh no, I should have clicked that button. I can find out what's running, just the app on port 80, and so on. But what's more useful is actually being able to see this application to join up and see the structure of the application. So I'll load up the app. So running locally on my laptop. And let's buy some socks. Who wants which socks? Colorful ones? Yeah, all right. Colorful ones are very popular. Pretty much every time I do this demo, people want the colorful ones. Okay, so I've added the socks to the cart. I've got 3 items in the cart. Proceed to checkout. Okay, so that's enough. So what we should see here is, in a second, we should see that some of those different components start sort of joining up. And, well, sometimes they do. I'll show you a stress test as well when we deploy this in production, and we might get more luck seeing that happening. Okay, so next. So let's just talk about what just happened. So I'll take you through. So this is what Scope is supposed to look like when it joins up. And actually, to generate this picture, I ran a load test on the application. So it caused all the different pieces to talk to each other. And Scope was able to detect the network connections between them. The Scope probe actually introspects what's happening in the kernel. It scrapes the output of /proc at the moment. We're working on an eBPF implementation that's going to be much more efficient than scraping proc. But basically, it's able to figure out, even when a container is running across containers are running across more than one host, it's able to show you all the connections between them in a live sort of fashion. So what happened when I put those colorful socks in my basket was that requests were coming into the front end. Then they were going to the catalog service to list the items in the catalog. I added things into my cart. That went into the cart service with the cart database. Then I connected to the login service, or I would have done, which connected to the account service, which connected to the orders service. So you can see it's very microservices-y. We've split it up into as many different pieces as we could. Let me just switch to this view, sorry. So of course, each service is small, simple, and self-contained. Each service can be maintained by a separate team and upgraded and deployed independently of the others. Each service that has state obviously needs to have its own independent database so that those database schema upgrades don't need to be synchronized across different teams. And so we're trying to decouple things as much as we possibly can. And of course, different teams can use whatever language they want. Okay, so let's take the app that I've got up and running on my laptop and deploy it to production. So in order to do that, I'm going to spin up a Kubernetes cluster. I'm going to use a tool that we got involved in helping out working on called kubeadmin. And I'm going to install WeaveNet as part of that application, as part of that deployment. WeaveNet is a container network. It's one of the tools that we develop. And it allows containers on different hosts to find each other and talk to each other. And it can be installed as a pod network as part of the setup of Kubernetes. So who here has heard of Kubernetes? Okay, so most people. For those who haven't, who here has heard of Docker? Okay, everyone's heard of Docker, cool. So what I just showed wasn't completely baffling, hopefully. So Kubernetes is, just very quickly, a container orchestrator that builds on top of Docker. So Docker is just a container runtime that will sit on a single host, typically, although they are now adding orchestration to the Docker product as well. But back when Docker was just single host, Kubernetes started as a project from Google to manage containers across a fleet of machines, a set of machines. And so you create, well, I'll show you rather than just talking about it. Okay, so in order to, that's visible, right? Okay, great. So in order to spin up a Kubernetes cluster, I'm going to get some computers. I'm actually just going to be following a guide that we wrote on the Kubernetes docs. So before we started working on this, so before we started working on kubeadmin, which is this tool that now ships with Kubernetes, Kubernetes was notoriously difficult to install. I see some nods. Some people have tried installing Kubernetes clearly, and they felt the pain. I tried it once. It took me about 3 days, and I ended up debugging. Anyway, there was the version of the kubelet was secretly different, even though all the kubectl version stuff was telling me it was running one version, but the kubelet was running a different version because it was on CoreOS. But anyway, that's a whole other story. But kubeadmin makes it insanely easy to install Kubernetes. At least that's the goal. And it just requires some computers running Linux, which is a nice sort of baseline. Everyone knows how to get computers running Linux. And everyone probably has their own way of wanting to get computers running Linux, depending on their environment. So some people might want to use Terraform. Some people might want to boot up Raspberry Pis. Other people want to use vSphere in their own data center or whatever. So today I'm going to use DigitalOcean. And I spun up 3 VMs earlier, and here they are. I promise I haven't done anything to them apart from turn them on. So these are completely fresh. So I'm going to just log into each of the VMs in turn. I'm going to do this trick so I can type the same thing into all the VMs. So these are just Ubuntu 16.04 VMs. So I'm going to start by installing the Kubernetes packages. Okay. And that's just an apt repo, which is nice and simple. Won't take long. And so let me just move on to the next step. And so the structure of Kubernetes is that it has a set of machines that are masters. In this example, I'm going to use a single master, and then a set of machines that are nodes. And the nodes are where the actual workloads run, typically. So the containers that you deploy to the cluster will run on the nodes. The master runs an API server, scheduler, controller manager, etcd, cluster database, and various other bits. Okay, so I'm going to go out of synchronized mode now because I'm going to do different things to different machines. So the first thing I'm going to run is this new kubeadmin command that, as I mentioned, we got involved in helping out on. And we're going to run kubeadmin init. And so what that's done, it's generated a random token that acts as a sort of bearer token or a shared secret between the different machines. And that allows the different machines to authenticate to each other securely. So it's then setting up public key infrastructure, so it's generating certificates, and it's then waiting for the control plane to become ready. And what that's doing under the hood, that's started up the kubelet. The kubelet is the sort of the beating heart of Kubernetes on each of the machines. It's responsible for actually running the containers. As that control plane becomes ready, what that means is that the API server, the kubelet has started up the API server using static pods, which are statically configured on that master. Because this is sort of a bootstrapping problem, we need to get the thing up and running. And then it spits out this command, which you can go and run on other machines. And so kubeadmin join, what that's going to do is it's going to say, okay, I'm being told a token and the address of a master. Armed with that information, I can go and reach out to the master, and I can use JWT, which is a cryptographic protocol for exchanging signed and encrypted information between peers, and say, hey, without actually sending the secret, which is the second part here, over the wire, it does crypto to establish trust between the different machines. And then using that trusted connection, it sends, it does TLS bootstrapping handshake. So we'll see that now. I'll just run this, and it's really, really quick. It's just doing that little transaction. It didn't need to download anything on the nodes because the kubelet was already running there. And what that did was it asked the master, hey, I'm a new node. I know this token. I can prove it to you, even without telling you the token, using crypto. And I'd like to join your cluster, please. And the master in a kubeadmin setup by default is configured to automatically accept any certificate signing requests that come from new nodes. There would be an alternative mode here where an admin would have to say, look at a list of nodes that have requested to join and be like, yes, that one's okay. I can match that up somehow out of band with that machine over there, so I'm definitely secure. Okay, so I can now use kubectl on the master, and I can do kubectl get nodes, and I can see that I've got 3 code mesh nodes. up and running, ready to run workloads. So my cluster isn't quite ready yet. What I now need to do is install a pod network. And as I mentioned, here it is. That's the link I was looking for. So as I mentioned, WeaveNet is one of those available pod networks. One of the nice things about WeaveNet is that it uses gossip and CRDTs to avoid requiring a central store. And actually, just late last night, I was recording a demo of federated Kubernetes that uses a single WeaveNet across multiple clouds, which I won't show now because I probably won't have time, although if we do have time, I can show you if you're interested. But so the federated Kubernetes really needs to not have a single data store, because you don't want your network to be beholden to an etcd cluster that's running like in one specific cloud or in one specific data center. So anyway, without further ado, let's go and install that, that network. And one of the cool things about Kubernetes now is that you can install a CNI network with a single command. And that deploys the CNI network across all the nodes as a daemon set. And in Kubernetes, a daemon set is just a pod description. Pods are sets of containers. And so a daemon set is a set of containers that are just told to run on all the computers. So this is useful for like system services that need to run on all the machines. And we've also got a daemon set for scope, which I'll show you in a minute. So, so in this way, we're able to set up a Weave network. And if we, let me just find this. So if we now run kubectl get pods all namespaces, the way that you tell that your network is up and running is when your kubedns pod goes to running, because DNS depends on the network. So we've got a Kubernetes cluster up and running. It was actually very little typing, even though I talked a lot, so that's an improvement on where it was before. And now we can try deploying the socks shop. So actually, as part of this, we've got some configuration for the socks shop in this tutorial. And this is all on the official Kubernetes docs, by the way, so you can try it at home. So I'm going to start by creating a namespace. Namespaces in Kubernetes are like different workspaces. They can be different security contexts, and basically they're like environments in which sets of other API objects exist. And now we can apply to that namespace this manifest file, which, while that's applying, I can show you. And so this is very similar to the Docker compose file we saw earlier. It's really just a list of all the bits. And hopefully we've got node port. No. Okay. Okay. So we should be able to do kubectl get pods -n sock shop. And we can see that some of those containers are still starting up. That just means they're downloading the Docker images, probably from the Docker Hub. And very shortly, we should see those go to running. I'm just going to check. Oh, yeah, it is a node port. OK, I don't know why that didn't show up in the config. But because this cluster is just running on DigitalOcean on machines running Linux, it doesn't have any cloud provider integrations configured. Kubernetes does support cloud provider integrations, so you can do things like automatically provision EBS volumes on AWS for stateful services, which is pretty cool. They can then follow the container around like databases, because databases like having their data. You can also automatically provision load balancers using Kubernetes and various other bits and pieces. But we're not going to do any of that fancy stuff today. We're just going to use what's called node port, which is like an alternative to a load balancer. Node port just says, hey, give me a port on all the machines and route that port on all the machines to a specific service. And so if we don't specify what node port we want, then Kubernetes just randomly allocates one for each service in the high range of port numbers between 30,000 and 33,000, I think. Okay, so let's see. Our shop might now be up and running. Okay, it is. So this is the moment of truth. So that's the port I want. I can pick any one of these machines and go to the IP address. And huzzah, we have our socks shop up and running. Or hopefully. Well, we don't have any socks yet. Sometimes it takes a minute. While that's running, while that's starting, there we go, we've got our socks, excellent. So while that's starting up, we can also deploy Wevescope, which is listed here in the list of add-ons, which is the same UI I showed you earlier. And so using this command here, I can also deploy scope on my Kubernetes cluster, just like I deployed it locally on my laptop when I showed you the laptop demo. And the token I need is in WeaveCloud, which is here. So I'm going to switch to a different instance in WeaveCloud, which is also a bit like a workspace. And I'll switch to the Kubernetes demo instance. And I haven't plugged anything in yet here, so I'll plug those service tokens in. We'll plug that service token in. And that's created another daemon set. So again, the Wevescope probe is going to run across all the machines. It's going to figure out what containers are running here. It's also got integration with Kubernetes API, so it can show things like pods, replica sets, etc. And any moment now, we'll see the probes show up. They take a little time because it's downloading the Docker images for Wevescope as well as we speak. So let's just give that a minute. Oh, okay, our first machine has shown up. I'm expecting 3 of them to show up, so I'll probably get a random distribution. Okay, that's probably enough to get started. It should. Okay, cool. So already the promised joining up that I failed to achieve in the laptop demo has already started happening here. So we can see already that the front end is talking to the cart and the catalog, and the catalog is talking to the catalog database, and the cart is talking to the cart database, and that's all good. We don't have everything fully joined up in this application yet, and that's because we haven't actually pushed any traffic through the application yet. I should be able to run a quick load test, if I can remember where I put it. And this is a Python program, so I need to do something with the virtual env, and I don't have it in my history, so I'm going to have to figure out how to run it again. Sorry about this. Okay. So let me just look on the Microservices demo repo. So there are some instructions in here for running a load test. There we go. And if I recall correctly, I can run a load test against the app there. Just while that warms up, we can also go through and buy some socks, colorful ones. Anyone else for any other type of socks? Which one? Holy, yeah. I like the holy ones. Although they are $99, I'm pretty sure I don't have that much on my credit card, so I'm going to have to say. Seriously, there is a limit built into the amount that you can buy in any one transaction. Okay, so I've logged in as a user. I'll try the Holy Socks in a minute, but here I'm just going to get the colorful ones, proceed to the checkout. And let's go and see. Yeah, okay, so we can see that the front end is now connected to the user service when I logged in. So we get this sort of live display of what's going on. And that's kind of nice. Okay, so I think that's everything I wanted to show in the Kubernetes app, in the Kubernetes demo. So just to recap, we installed Kubernetes from scratch on some machines on DigitalOcean. We then deployed the same Sock Shop application that we'd built as a set of microservices. We then deployed Wevescope. As part of installing Kubernetes, we installed WeaveNet, which allows the containers to even talk to each other. Then we installed Wevescope, which was able to push information about which containers there were and which ones were talking to each other into this Weave Cloud application. So that's that demo. So I've got a little bit more content. If I can find the right button. Yeah, so to recap, we started out with Docker for Mac. We used a compose file there. Docker Compose, for anyone who doesn't know, is a fairly simple tool which allows you to define in a nice friendly YAML format. Here are the things that make up my services, and where things are containers with image names that get pulled down and define the connections between them. And then we used Wevescope plugged into Weave Cloud to push the information about those containers up to that UI I showed you. Then in Kubernetes, we spun up a Kubernetes cluster from scratch using that kubeadmin tool that, as I mentioned, myself and some of my colleagues at Weaveworks worked on with the Kubernetes community. Then we spun up the Sock Shop using the Kubernetes manifest, which is kind of like an equivalent to the Docker Compose that we saw earlier. We deployed WeaveNet using a daemon set, and then we also deployed Wevescope probes using a daemon set and plugged those into Weave Cloud as well. So I'm going to talk a little bit about WeaveNet because developing WeaveNet was kind of interesting. It's a pod network. What that means it's described as a pod network in Kubernetes because Kubernetes has sets of containers that are pods that want to be able to talk to each other. And the idea is that it gives each pod or each container its own IP address on an overlay network. So it forms an overlay network between the hosts using gossip and CRDTs to share information between the nodes. And then it does IPAM, so IP address management. So it allocates a set of IP addresses to each machine, and it can dynamically reconfigure which IP ranges exist on each machine. And then out of those IP ranges, it can automatically allocate IPs for containers that come along. And Kubernetes plugs into it via what's called CNI, which is the Container Network Interface, which is a standard way of plugging in these network providers into Kubernetes. And I want to take a brief digression to talk a little bit about how WeaveNet works under the hood. So we factored out, under the bonnet, I should say. So we factored out a lot of the more interesting gossip and CRDT logic in WeaveNet into a separate Golang library that we call WeaveMesh. And so if anyone wants to play with gossip and CRDTs and build their own distributed system that uses them, then you can just pick up WeaveMesh and use it as a Golang library and vendor it into your project as you normally do. So yeah, this is a library that's used by Net and also WeaveDNS. And there's some kind of interesting computer science in it, and this sort of audience may already know this, so I apologize if I'm repeating things that you already know. But so Alexis, our CEO, likes to describe WeaveNet as being invincible, like you can drive a truck over it and it carries on working. And I pretty much agree with that, because with most of the container networking options out there, they rely on a centralized data store. And that centralized data store is something like etcd. And etcd uses Raft. And Raft favors, it favors CP in the CAP theorem. So it's consistent and partition tolerant. And that means it sacrifices availability in the face of network partitions, right? So networks have network partitions all the time. You want your network to carry on working if you have a network partition. Normal networks do. Things like BGP, which are like how the internet works, are available and partition tolerant for exactly that reason. The internet would not scale if there was a big centralized database of all the IP addresses somewhere. So we kind of feel sort of righteously indignant about, or whatever, about the fact that this is actually the right architectural model to use, both for IP address allocation as well as things like service discovery. And so how that works with WeaveMesh is that you might have a set of machines like this. So let's assume these are processes that are running on different machines, each of the red boxes. And so the goal here is that we get all the machines to agree on what the number is. So let's assume that there's one sort of value that we're trying to get everyone to eventually agree on. And so gossip is this approach to communication in a distributed system which favors eventual consistency. As you know, the network is not reliable. And the basic idea here is that even if there's a partition between the top left and the top right nodes in this network, and note that this is a partial partition, it's not a complete network partition, then by gossiping with each other about what they know, then the guy in the top right will eventually be able to learn about the value that was given to the node in the top left. And so that all seems pretty trivial. That would be a simple algorithm to implement, like, I learn a value, tell my peers. But obviously it's not that simple. That only describes the communication model, which isn't enough. Because if someone updates the top left with value 1 and the top right with value 2, and then those values meet in the middle, then the question is which one is right. If you're favoring this eventually consistent model, then you can't assume that you've achieved quorum on any value that you think you're going to agree on ahead of committing it to a node. You just have to go ahead and commit it and then hope that it will propagate. And so you have to resolve conflicts. You need data structures and algorithms that can always figure out how to resolve a conflict. And so, as you can see, the message may need to be gossiped many hops, and it's not clear which one will win. And what's more, you're going to have to deal with a dynamic network which is experiencing partial failure constantly, like the internet. So the network is coming and going, and messages will inevitably end up out of order or be repeated or be delayed. So CRDTs are a solution to this problem. And the solution to the problem is to be clever about the data structure that you're gossiping. And basically so that when you get updates, they can always be merged irrespective of how and when they arrive, and whichever order the updates arrive in, everyone always comes to the same idea about what the state of the system is eventually. And so CRDT stands for conflict-free replicated data type. And you define a data structure appropriate for your app, and you define this merge operation. Where you see the circle with a plus in it, I'm going to pronounce that merge. And merge is associative, which means that you can do B, then C first, and then merge A later, or vice versa. It's commutative, which means that A merge B is the same as B merge A. It's idempotent, which means that you can do it twice and it doesn't change. And so, at least to me, sort of intuitively, these requirements on the data structure and the merge function in particular make sense. Because if you have this merge operation, then messages can flow around the network in any order They can get missed, they can get reordered, they can get delivered 3,000 times, and your system will still converge on the same idea of what the current state is. And so this is really valuable if you build systems like WeaveNet that do IP address management, that do service discovery, that figure out how to route a message around in a network. It's really useful to be able to do this rather than depending on a central data store. And by the way, this is how Google Docs works. So if you've ever made some changes while you're offline and then someone else has made some changes to a doc and everything just seems to work, it's because Google Docs is implemented in terms of CRDTs. So some examples of CRDTs. So I talked in general about the requirements for the data structure and the merge operation, but some concrete examples are an add-only set. So an add-only set is pretty trivial, although arguably not that useful, depending on the application, because the merge operation is just union. So if you are holding on to some local state and you get a new message saying, here's the update, then you can just union the two sets together, and you'll satisfy these three requirements. You can also have a latest value in singleton, which is useful if you just want to store one thing. We did a prototype actually of kubeadmin, which unfortunately didn't make it, that was going to use CRDTs and mesh, in which the cluster's CA cert, the one that sets up the trust between it allows the nodes that are joining the master to trust that the master is who they claim to be, because they've had the CA cert sort of given to them somehow. We were going to gossip the CA cert over a secure channel, and in that case, the CA cert would be an example of a latest value in singleton, because you can just attach a timestamp to it, and then if you hear about a newer CA cert, then you can just replace the one that you've got. So you can satisfy those requirements. If you want to implement a set with deletion, i.e. a set that you can add items to and remove items from, then that's a little bit trickier, but you can give every element an ID, sort of like a UUID, and then maintain a separate add-only set of deleted items using an add-only set. So you can implement these more complex CRDTs in terms of the simpler ones. And there are lots more. So the link there is to an interesting experiment using defining CRDTs on arbitrary JSON documents. So I'm almost out of time. I'll push on through the rest of these slides. So if you're interested in implementing something in using WeaveMesh, then in general, the form of an update from a peer is like A merge B becomes C, where A is the update. The update could have been delivered twice or come in any order. B is the current state stored in memory or on disk on that process. And then you just need to define these three Golang interface methods. So merge received, merge delta, and merge complete. They all update the local state to C, but they differ in that merge complete returns C, merge received returns A, and merge delta returns the delta from B to C, which notably isn't just the update A, because the definition of merge might say something like throw away an update to one part of the data structure if the incoming update is out of date. So merge delta was the only one I really had trouble getting my head around, but that's how it works. It's not really that complicated. And so anyway, when applied to WeaveNet, which is one of the tools I showed you in Kubernetes, like I say, it doesn't need a centralized store. It carries on working during network partitions on both sides. So you can do IP address allocation on both sides of a network partition, and then when you heal, you carry on working. And like I say, it's particularly interesting in federated clusters. So I'll leave it there. There are some URLs if you want to try this stuff yourself. And thank you very much.
We have time we could do one question.
No questions? Oh, yeah.
A question about the security. So you've got the certificate kind of infrastructure there. and that's great for kind of creating TLS connections and what have you. Is there a kind of a good solution for securing UDP traffic between different components?
Yeah, so it's a good question. So the security, there are sort of two different aspects to security. The first one I showed you, as you mentioned, was the TLS certificate dance between the different Kubernetes components. But if you have UDP traffic, then you can just run it over WeaveNet, because WeaveNet operates at layer 2. It emulates a switch, so it's pretty easy to comprehend. It's an overlay network because it runs layer 2 over layer 3. That means you can run anything that you run on your layer 2 network over WeaveNet, and so you can run UDP over WeaveNet. That works great. You can also run multicast over WeaveNet, which is interesting. We have some customers in finance who are doing that for like stock trading, and that, for example, means that you can use multicast on AWS, which wasn't possible before. Kind of interesting. And just one last thing, WeaveNet also has encryption built into it, so you can give all of your peers a shared secret and they'll encrypt all the traffic, so you can do encrypted UDP between containers.
Okay, let's thank the speaker again.
Cool.